मॉर्निंग एवरीवन। कैसे हैं आप लोग? हाउ आर यू ऑल? इज माय वॉइस क्लियर? इज इट ऑडिबल? ओके देन से यस और नो। इज इट ऑडिबल? एम आई ऑडिबल टू यू? ओके, Ayushi, okay, it's audible. So now move further. Today we are going to start dual nature. This is the starting point of modern physics. The topic itself says dual nature of light or dual nature of particle. There is a fight between whether light is a particle, light shows particle nature, or light shows wave nature. There are few phenomena which shows light has wave nature, like interference, diffraction, polarization. These all phenomena shows that light has a wave nature. But when it comes about photoelectric effect, it shows that light has a particle nature. So the conclusion is the light has dual nature. This is concluded by de Broglie that light has dual nature. So we are assuming it to be a dual nature. So now in this chapter, we are going to discuss about photoelectric effect. And in this effect, we will discuss that light has particle nature. Clear. Moving further. So what are the topics that we need to discuss here? What is photon theory of light? First of all, we will discuss with that work function, experimental studies. Then there are some graphs and de Broglie wavelength is the final conclusion. Good morning, Chandrasekhar. Okay. So now first thing is photon theory of light. What I am saying, in this theory, light is assumed to be consisting of particles. And these particles are called as photons. Give me 1 second. Okay. So what I am saying, that light is made of particles, and these particles are known as photons, and these photons are also called as packets of energy. So what is mentioned here on your screen, light is quantized and carries energy in discrete packets known as photons. These photons are generally called as energy packets. Energy packets. Clear. Now again, if they are energy packets, then they must contain some amount of energy, and that energy is given by E is equals to H into F. What is saying? For an electromagnetic wave of frequency F, the energy of each photon is H into F, where F is the frequency, H is the Planck constant. H is what? Planck constant. What is its value? H is equals to 6.6 into 10 raised to the power minus 34 joule second is the value of Planck constant. Now again you can see here, this is the golden formula that you should remember, energy of the photon. Each photon has that much of energy. If there are 100 photons, then total energy will be 100 times of that. Now again it can be written as H. Frequency is what? C by lambda. So another formula that can be formed here, Hc by lambda. Now what is C here? C is the speed of light. C is the speed of light, which is a constant that is 3 into 10 raised to the power 8. I think this is the quantity that everyone knows. So I am not writing it there. Now one more thing. In this chapter or wherever you study, energy has a unit of joule. That means this energy should be in joule. Now, there is one more unit of energy, which is electron volt, which is electron volt, or I am writing another unit as electron volt. This electron volt is a very small unit of energy. Joule is a larger unit and electron volt is a smaller unit of energy. So what is the relation between these two quantities? That relation you should also remember, and that relation is 1 electron volt is equals to 1.6 into 10 raised to the power minus 19 joule. This relation you should remember. Remember each and everything. Now, one more thing that is very important for us. While solving the questions, there is a possibility that most of the times you need to calculate this energy of photons using hc by lambda. Using hc by lambda, and most of the times it is to be calculated in electron volt. It is to be calculated in electron volt. So in that situation, use the relation E is equals to the product of H and C will be 1240 divided by lambda. Now, most important part of this thing is that lambda you should place in nanometer and E will be in electron volt. Now, are you getting what I am saying? If you place lambda in nanometers, then energy will come out in electron volt if you put Hc as 1240, 1240. This is how we generally calculate energy. Is it clear? Now, I will give you an example on the next slide. Moving further. Next point is photons are, this is a point to be remembered actually, nothing else. Photons are neutral and their rest mass is zero. Neutral means they don't have charge. They travel with the speed of light, nothing important, but very simple. Each photon has a definite momentum. They have some momentum. And what is the value of their momentum? P is equals to H by lambda. This is the value of momentum. H is again Planck constant. Again, another statement says more number of photons means more intensity of light. Now read it in different way. Different way. More intensity means more photons are reaching the surface in unit time. Now, how can you identify that intensity is increasing? In a simple statement, if I say, look at the simple statement. Let's suppose this is a bulb. Clear? This is a bulb, light bulb. And this is my hand. Light is coming from this bulb on my hand. Clear? Now, if I place this bulb closer to my hand, you can observe that intensity of light will increase on my hand. Intensity, it will become more brighter, intensity of light will increase. So there might be a question in which the question says that light source is placed closer to the surface. Whenever question says light source is placed closer to the surface, that means intensity is increasing. And whenever it says light source is placed away from the surface or moved away from the surface, that means intensity is decreasing. So this is the thing that you should relate and you should keep in mind. So till now, what we have studied. Now, the example thing that I was talking about, let's suppose a light has a wavelength of 600 nanometer. and they are asking you calculate energy of photon. Now, what you should do, energy of photon is equals to 1240 divided by lambda, that is 600. Now, you should not convert nanometer into meter. You should keep it in nanometer. You should keep it in nanometer. So that will be the energy. Clear? I think it's clear. Moving further. Now, one more thing. I am telling you, you should remember this. One more thing. Sometimes the question says, in this question, wavelength is 600 nanometer. But sometimes question says the wavelength is in angstrom. Most of the time, the wavelength will be in angstrom. Then what you should do? What you should do? Let's suppose that wavelength is given as 6000 angstrom. Now you have to convert this wavelength into nanometer. And to convert angstrom into nanometer, just put the decimal one place before. So it will become 600 nanometer. For example, there is mentioned as 1325 angstrom. Then what will be in nanometer? So you can say place decimal one place earlier, that will be 132.5 nanometer. These are the simple things and you should remember them. What is most compulsory? Place this value in nanometer. Nothing else. Clear? I think everything is. Moving further. Work function. Definition is on your screen. What it says, the minimum energy required to just eject an electron from a metal is called work function. Listen to me. It is denoted by psi, or someone might denote it with phi, or someone might denote it with W or W naught, whatever, phi or phi naught, whatever. But the term I am using for work function in this whole lecture is going to be psi. What is it? Psi. Psi denotes work function. What it says, the minimum energy required to just eject an electron from a metal. This is a metal surface. So if I want to remove one electron from it, the electrons are bounded from the nucleus in an atom. And if you want to remove that electron, you must give some energy to it. And if I give energy, so the minimum energy required to eject an electron is called work function. I think this definition is clear. What is the unit of work function? Work is measured. The work is what? Work function is what? Energy required. So its unit is again joule. But we are not going to use joule. What we use? We will use electron volt. We will use electron volt as the unit. And you know the relation between electron volt and joule. Moving further. Now, one more important thing, very important thing that will clear the concept of photoelectric effect. Let's study here. What is photoelectric emission? Now, listen to me. Read the definition after a while. What I'm saying, let's suppose this is a metal surface. This is a metal surface. And some light is incident on it. And due to this light, if electrons comes out, if electrons of the metal comes out, then this process is known as photoelectric effect. Then this process is known as photoelectric effect. That means emission of electrons with the help of incident light. Now there are some keywords here in the definition. When an electromagnetic radiation of suitable frequency, this suitable frequency is called as threshold frequency. We will discuss it, is called as threshold frequency. Now, falls on a metallic surface, electrons come out of the surface. This is known as photoelectric emission. And this effect is known as photoelectric effect. And these electrons are called as photoelectrons. These electrons are called as photoelectrons. Now listen. Let's suppose the light which is coming has photons in it. And each photon has a energy E. Mind my words, each photon has a energy E. The work function of the metal is psi. Clear? Now what I am saying, let's take some values. Let's suppose psi is 2 electron volt and energy is 5 electron volt. Energy is 5 electron volt, energy of photon. What happens when a photon comes? Listen to me. When a photon comes, it strikes the surface. It transfers its energy to the electron. First step. It transfers its energy to the electron. The electron gains that energy and starts moving outward from the metal. And while coming out, it may collide with some other particles, with some other electrons. And in this process, it may lose its energy. Is it very difficult to understand? Or is it clear till now what I'm saying? Photon is coming, it strikes the surface and transfers its energy to the electron. After receiving the energy, electron gets excited and starts moving outward. And while it is moving outward, it may lose some energy in the collisions. It may lose some energy in the collisions. So now what I'm saying, assuming an ideal situation when the electron does not collide with anyone, it just came out without any collision. Now listen, then what will be its kinetic energy? If it just comes out, then its kinetic energy will be maximum, which is denoted by Kmax, is equals to the energy given by the photon is 5 electron volt and energy required to remove it or to come out is 2 electron volt. I have given you 5, out of which 2 is invested in coming out. So you have remaining 3 electron volt of energy. You have remaining 3 electron volt of energy. So that is how it is calculated, E minus psi. This is the most important and very frequent golden equation. You should mind it. This is a golden equation of this chapter. Kmax equals to E minus psi. Why I am writing Kmax? Because I have assumed that electron has not collided. But in fact, it may have collided. It may have collided with other electrons and loses some of its energy. So actually, what I'm saying, kinetic energy actually is always less than Kmax. Sometimes it may be equals to Kmax, but most of the times it's less than Kmax. Clear? But what is more important or most important is this equation. Remember it, write it right away. Now moving further. Experimental setup. Okay, K minimum is 0. If I am saying in the previous topic, K maximum is E minus psi, then what will be the K minimum? Very good question. K minimum is equals to 0. What does it mean? That electron, after receiving that much of energy, loses all its energy in the collision and just comes out. And all its extra energy is loses or is lost in the collisions. Clear? So K minimum is always 0. But K maximum is E minus psi, where E is the energy of photon, psi is the work function. Clear? I think. Okay, moving further. Now there is the experimental setup. What this setup says, let's suppose this is a glass tube which is vacuum. There is a vacuum inside it. Light is incident. When I am drawing light by these lines, it means that photons are coming. I am representing photons. The photons enters and strikes this plate. This metallic plate is termed as emitter, E for emitter. Why it is termed as emitter? Because from this plate, electrons will come out. When the light strikes, now listen to me very carefully, each and every word. Do you know this experimental setup? Should I move with some speed or should I explain it in little bit of details? Just tell me, give me a hint so that I can please explain. Okay. Now what happens? What I'm doing? First step, I have started with low frequency. That means the incident light has a very low frequency. And what I did, this is a battery. This arrow indicates its potential can be changed. So right now, this collector has a potential positive and this emitter has a negative potential. Now what I did, incident a light of very low frequency and increased this potential, and see there is no current in the microemitter. In the emitter, you can say there is no current in the emitter. That means no electron has come out. Now what I did, I have increased the frequency a little bit, increased, increased, and increased. And after this, at a certain frequency, what I see that there is a current in this emitter, which indicates that after a certain frequency, electrons come out. And this certain frequency is known as threshold frequency. This certain frequency is known as threshold frequency. This is again a very important term that we will discuss in definitions right after this experimental setup. So now listen to me. Now, assuming that electrons are coming out, at which frequency? After threshold frequency, electrons are coming out. Now listen. The electrons which are coming out of this metal, I can divide these electrons in three categories. I can divide these electrons in three categories. First category is maximum kinetic energy electrons. I am not writing it. I will just tell you what are the three categories of electrons that may come out. One, that have maximum kinetic energy. Second, that have some less kinetic energy. And third, which has zero kinetic energy. K minimum, that thing you were asking. Three categories of electrons will come out. Maximum kinetic energy. Maximum kinetic energy. Second is medium kinetic energy. Third is zero kinetic energy. Now listen. The electrons which have maximum kinetic energy will automatically move towards the collector because they have some kinetic energy and they itself can move towards the collector. The electrons which have some lesser kinetic energy are midway in this tube, and the electrons which have zero kinetic energy are just standing there. They are just standing there. So there is three variety of electrons. Now, if I increase this potential, collector potential, this becomes positive. This positive potential will attract all the electrons, and these all electrons will start moving towards the collector. If I further increase this collector potential, then a situation comes when all the electrons emitting will reach the collector. And in this situation, the current is known as saturation current. Saturation current. This saturation current is going to be used a lot of times in the discussion on the next slide. So what is saturation current? When all the electrons emitted reaches the collector. All the electrons emitted reaches the collector, then the current is known as saturation current. Now, one more point that I will add here. If you can understand, if you remember the punchlines from the previous slides of the photon theory, now what I am doing, if I increase the intensity of light, then what will increase? Tell me. If I increase the intensity of light, then what will increase? Do you remember there is a punchline mentioned of in photon theory of light? Tell me, I am on standby. If intensity of light is increased, then what will increase? You can say yes or no as well. I don't know. I forgot. You can say anything like that. Forgot. Okay. Listen. Whenever the intensity of light increases, it means number of photons are increasing. It means number of photons are increasing. Now remember it for the rest of the time. If intensity increases, that number of photons increase. Now listen. If number of photons are increasing, that means photons were giving the energy to the electrons. That means number of electrons emitted will also increase. Number of electrons will increase. That means current will also increase. So finally, the verdict is if intensity increases, then saturation current increases. Clear till now? Now there is one more thing that is to be discussed, and that another thing is stopping potential. Stopping potential, listen. Very good, Veena. Veena says correct answer, photon. Very good. Now, stopping potential. Now, what I am doing, let's suppose I am changing the terminals of this battery. This becomes negative, positive, negative, positive. That means I have changed the terminals of the battery now. So this collector becomes negative. Keep everything in mind. If this collector becomes negative, then can you see that this collector will repel the electrons and oppose the motion of electrons towards itself. Oppose the motion of electrons towards itself. So what is the stopping potential? The minimum negative potential of the collector. The minimum negative potential of the collector at which fastest electrons just fails to reach the collector. This is a very difficult definition to remember. What I'm saying, remember in Hindi. These are the electrons moving towards collector. It is not Hindi. These are the electrons moving towards the collector. If I apply negative potential at the collector, then it will oppose the motion of electrons. So the minimum value of potential at the collector at which the fastest electron is not able to reach the collector is called stopping potential. The definition is mentioned on your screen. The minimum negative potential of collector at which highest energy electron just fails to reach the collector is called stopping potential. It is denoted by V naught. What is V naught? The formula is on your screen. But if I say the golden relation that you should again remember is K max is equals to EV naught. This is the golden relation. K max is equals to EV naught. What is the significance of this equation? Remember everything. If I say stopping potential is 3 volt, what's happening? The stopping potential is 3 volt. Then find K max. This is a very common question. If the stopping potential is 3 volt, then what is K max? What you should do, K max will be 3 electron volt, nothing else. Just place E in front of stopping potential and it will become K max. So there is a relation, something like that. If V naught is 3 volt, then K max will be 3 electron volt. If V naught is 5 volt, then K max will be 5 electron volt. Is everything clear? And now remember this equation. V naught is equals to HF by E minus psi by E. This is nothing else. I have placed the value of Kmax, which is E minus psi, and divided by this E, that is HF by E minus psi by E. Clear? One more thing that is to be remembered. In this equation, you can see stopping potential depends on frequency. Depends on frequency. And you can say stopping potential is independent of intensity. This is a very important punchline. The stopping potential is independent of intensity. So in this slide, there were two or three things. One is what is stopping potential. Another is golden equation, Kmax equals to EV naught. Next is formula for V naught. And what is the purpose of this equation, Kmax equals to EV naught? Can you see that inverse is also going to be true? What if I say, take a deep breath and listen again. What if I say that maximum kinetic energy of the electron is 5 electron volt? Then what will be the stopping potential required? You will say kinetic energy is 5 electron volt, then stopping potential will be 5 volt. Reverse is true. This is a very important question. Mind it. Moving further. Threshold frequency. Now there are some basic formulas. What is threshold frequency? The minimum frequency at which photoelectric effect starts. At which photoelectric effect starts. Now, remember this another definition which is also very important. The frequency of incident light at which maximum kinetic energy of emitted photoelectrons is 0. That means the emitted photoelectrons just come out without any energy. They just come out of the metal and stand like that. They don't have energy to move. So in such situation, the frequency is known as threshold frequency. It is denoted by F naught. And the formula for that F naught is on your screen, psi by H. Important relation. Now, one question that I am asking. The threshold frequency for a surface is given as 700 nanometer. It is given. And they are saying that a light is incident of frequency 600 nanometer. Will the photoelectron come out or not? Will the photoelectron come out or not? Say yes or no. The threshold frequency is given. This is the threshold frequency. And light, which is incident, has a frequency 600 nanometer. Will photoelectrons come out of this surface or not? Please answer. Gauri, yes. Chichuni is saying yes. Anyone else? Veena is saying no. Very good, Veena. Now, Gauri, what is your take? Listen, the statement itself says this is the minimum frequency. Minimum frequency means if the incident light has a frequency less than that, then no photoelectric effect will take place. Minimum means after this frequency, only photoelectric effect will take place or electrons will come out. So that means the answer is no photoelectron will come out. This is the result. Can you see this moving further? If there is a threshold frequency, then there is a term known as threshold wavelength as well. Threshold wavelength. Now you can see that the relation is F is equals to C by lambda. They are reciprocal to each other. That means if frequency is minimum, then wavelength will be maximum. So the definition itself changes to the maximum wavelength at which photoelectric effect starts. The maximum wavelength at which photoelectric effect starts is known as what? Threshold wavelength. What is the formula for that? Lambda naught is equals to hc by psi. Again, remember hc. What is the value of hc? I told you. What is the value of hc that I told you to put? Tell me quick. What is the value of hc? इतनी जल्दी भूलोगे तो कैसे होगा? Then this is a wastage of time, na? If you forgot this value hc, very good, Veena, 1240. What you guys doing? Dhruvi, Gauri, Ritu, Vana, Chandana, what you guys are doing? You don't remember the value of hc, that is 1240 that I have told you. It will ruin everything, na? After completing the session, I have put so much of energy in this. Then after completing the session, you should know everything. Take a pen and paper with yourself. Otherwise, I am going to ask you that turn on your camera and show me where is your pen, where is your notebook, everything like that. It's not going to be tolerated anymore. That you are not answering a simple term which is 1240. Don't make me angry. Don't make me feel like you are just sitting and not doing anything. Be attentive. Moving further. Now there are some graphs. Most of the times questions were asked from these graphs. So make your mind. What is this? This I is the photocurrent. V is the potential. Potential of what? Collector potential. This is what? Collector potential. This point indicates above this positive potential, below this the negative potential. That means collector is made negative. This is zero potential. This point shows zero potential. Now, what if I say the graph varies something like that? At this point, the current is zero. At this point, the current is zero. And this point at which current is zero is generally known as, or you called it as, stopping potential. So this point indicates stopping potential. Clear? This point is indicating stopping potential. And in this region, you can see that if I increase the potential, you can clearly see that current is increasing, and at a certain time, it becomes constant. So this region is representing saturation current. Saturation current. Clear? I think in this graph, every point is clear. Now tell me one thing only, that at zero potential, there is a certain value of current. Why there is certain value of current at zero potential? Answer me in the comment box. Why there is a certain value of current at zero potential? I am moving on the next slide. Now, again, the graph is between same photocurrent and collector potential. Now the statement changes at various intensities. They are telling us to draw this at various intensities but constant frequency. Now listen very carefully. One thing to be clear, if I increase the intensity, a punchline is there, if I increase the intensity, photons will increase. and which in turn increase the current, which in turn increase the current. That means current will be increasing. This point is stopping potential. And I mentioned you that stopping potential is independent of intensity, where I have mentioned on the previous slides. That means the graph will be something like that. Now, let's suppose this is at intensity I1, this is at intensity I2, this is at intensity I3. What does it mean? Out of these three, which intensity is more? Because current is more for I3, so what is the conclusion? I3 is greater than I2 is greater than I1. I3, I2, I1 are the intensities of light. And you can clearly see that saturation current is increasing as we increase the intensity of light. Remember this in mind. One more thing. This point is the stopping potential. And stopping potential is independent of intensity. That is the punchline that I have mentioned earlier. Moving further. Again, the same graph, but the question this time says at various frequencies but constant intensity. If intensity remains constant, that means saturation current will remain constant. Now, what about frequency? You know the relation, or you must know the relation V naught is equals to HF by E minus psi by E. This is the relation for stopping potential. If frequency is increased, then stopping potential will also increase. That means if I increase the frequency, then stopping potential will also increase, but the graph will something look like that. This is for frequency F1, this is for frequency F2, this is for frequency F3. Out of these three, which frequency is more? F3 is more, F2 is more, F1. But the saturation current will remain constant. Clear? One more graph. V naught versus F. V naught versus F. Now listen to me again very carefully. The relation between V naught versus F is, okay, you don't know this equation of a straight line, so I am not expressing in that terms. What I am telling you, remember this thing. This point is known as threshold frequency. The point at which it cuts the x-axis or the frequency axis is known as threshold frequency. The slope of this graph is h by e. And this intercept is psi by e. Give me 1 second. Okay. The slope is h by e, which is a constant term. Now, I don't know whether you are understanding it or not, but you should remember this in terms of V naught versus F graph. V naught versus F graph, the slope is h by e. Let's suppose this one more thing. If there were two metals, metal A, this is metal A, and this is metal B. If for two surfaces, I want to, what is this? I want to draw this V naught versus F curve, then one thing is very important. The slope is a constant. That means slope will remain same. And the two graphs for A and B will remain parallel all the time. This is for metal A, this is for metal B, will always remain parallel. Why become parallel? Because the slope is a constant. So all the graph will remain parallel. Clear? So now tell me, out of these two graphs, which metal has higher threshold frequency? A or B, which has higher threshold frequency? A or B, which has higher threshold frequency? Anyone who can answer that? Graph A cuts the frequency at this point. Gauri Lakshmi is saying B. Very good, Gauri. This is the second graph, B. This is the point now. So on this axis, if you see, this is the threshold frequency of first one. This is the threshold frequency of second one. That means threshold frequency of B is greater than threshold frequency of A. If threshold frequency of B is greater, that means threshold wavelength will be lesser than. That means lambda naught of B will be lesser than lambda naught of A because they are reciprocal. So from this graph, lot of conclusion can be made. Moving further. Similar is the graph for Kmax versus F. What's changing? In this graph, the slope is H. This point is again F naught. This point is psi. And again, slope is a constant term for any two metals. Graph will be parallel. Moving further. Very good, Veena. Einstein's photoelectric equation. This equation is known as Einstein Photoelectric equation, which we have studied earlier. Kmax equals to E minus psi. What is E? Anyone tell me? What is E? What is E? What is E in this equation? Be very quick. Very quick, very quick, very quick. I'm again saying Kmax is equals to E minus I. What is E? Energy. Okay. Energy of photon. Very good. This is energy of photon. Again, this equation can be modified in this term. Kmax is equals to H F minus F naught. H F minus F naught. Moving further. This is a equation that you should remember. Now there are punchlines. Take a screenshot of these punchlines. They are self-explanatory. I don't need to explain. I don't need to explain it. Just take a screenshot, and when you done with that screenshot thing, tell me, I will move further. Clear? I think it's done now. Okay. Very good. De Broglie wavelength. This de Broglie thing is again very important. I will describe you in a little bit of detail, not that much. What it says, de Broglie says that any particle, listen to me, any particle moving will show a wave-like nature. This is a very different thing. If you are moving with some velocity, then you are behaving like a wave. However, the wavelength will be something that is not to be considered, but you are behaving like a wave. Similarly, if an electron is moving, then this electron is behaving like a wave that you should have studied in your chemistry classes, that wave nature. That means moving particle, according to de Broglie, I am writing, moving particle behaves as a wave. And if they are behaving as a wave, then there must be a wavelength associated with them. So the wavelength is given by h over p, where p is the momentum. P is the momentum. So it can be written as lambda is equals to h over momentum is what? mv. One more form that can be written here, lambda is equals to h over. Now the relation between P and kinetic energy, you know the relation, I think. What is the relation between momentum and kinetic energy? P is equals to root 2 km. Generally, we remember the relation between P and kinetic energy as P is equals to root 2 kilometer. This is not kilometer actually. K is the kinetic energy, M is the mass. But we can remember it in this term, h over root 2 kilometer. Root 2 kilometer. This is the again very important term. I hope you are writing it. You are making the short notes. Moving further. De Broglie wavelength of electrons. Once again, they are talking about electrons. So if they are talking about for electron, what is the situation here? Situation says an electron is at rest and it is accelerated by some potential. Then what will be its wavelength? It is accelerated by some potential. Then what will be its wavelength? That is 12.27 by root V angstrom. Here V is the accelerating potential. Now again, I have told you this is in angstrom. If you want to calculate it in nanometer, what you will do? You will change this decimal towards left, or it will become 1.227 nanometer. I think this point is clear, was clear actually. Now there are only questions. Let's try to do it. How much you have learned? First question. It says the work function of a photosensitive material is 4 electron volt. Work function is denoted by psi, is given as 4 electron volt. Very good. The longest wavelength of light that can cause photoelectric emission. Whenever they are talking about the largest or longest wavelength, they are talking about threshold wavelength. They are asking me threshold wavelength. So what we know, threshold wavelength is hc by psi. Hc by psi. I think you know the relation now. So you know the value of hc is 1240. Psi is what? 4 electron volt. So lambda naught will be 310 nanometer. 310 nanometer. Very simple question, doable. Asked in the NEET exam. And recent NEET exam, I think 2019, it was asked. Moving further on another question. Why isn't it in angstrom? Okay. Listen. Whenever I place this value as 1240, then it is mandatory. I have calculated the values. H has some value, C has some value. Then after a lot of calculation, it is concluded, it is put that 1240, if you put, and this term is in electron volt or energy is in electron volt, then wavelength will definitely come in nanometer. It's not like that we should, there is nothing rule of that. This is a pure calculation that we have done. And I have done it for you. And after the calculation, I am putting this value in front of you, 1240. And if you want to calculate it in angstrom, then you should put Hc is equals to 12400. Then wavelength will come in angstrom. So we are not going to use that. We are going to use only 1240. Again, another question. Photon with energy 5 electron volt are incident on a cathode in a photoelectric cell. Okay. That means energy of photon is given as 5 electron volt. The maximum energy of the emitted photoelectrons is 2 electron volt. That means K max is also given 2 electron volt. From this relation, what I can conclude, we know the relation K max is equal to E minus psi. Put the value K max is 2, energy is 5 minus psi. So can you conclude psi is equal to 3 electron volt? From the first statement, I have concluded that thing. Now in the second statement, it says, when photons of energy 6 electron volt are incident, no photoelectrons will reach the anode if the stopping potential of A is this much. Again, listen to me. They are asking me the stopping potential. Okay. Now this time, energy is 6 electron volt. Again, if I calculate K max is equals to E minus psi. K max will be what? E is 6. Psi we have calculated already, that is 3. That is 3 electron volt. You know the value of K max and they are asking you the stopping potential. So stopping potential, I have told you, just remove this electron volt, the E term. So for the stopping potential will be 3 volt. But remember this thing, they are asking something different. The stopping potential of A relative to C. You know that stopping potential is the negative potential by definition. Stopping potential is the negative potential. So magnitude is going to be 3 volt. But with respect to the anode, with respect to the cathode, it is going to be minus 3. Why minus 3? Because the definition says it is the negative potential. So the definition says, according to definition, it will become minus 3 volt. Moving further, we will discuss one or two more questions. Two radiations of photons with energy 1 electron volt and 2.5 electron volt successively illuminate a photosensitive metallic surface of work function 0.5 electron volt. Very good. The ratio of maximum speeds. Now they are not talking about maximum energy, they are talking about maximum speed. No problem. What we know that K max is equals to E minus psi. So if I put it for first, K max of first surface, it will be, energy is what? 1 electron volt. Can you identify this? This is the energy of photon given now. 1 minus 0.5 work function. That means K max 1 is equals to 0.5. And K max 2 will be, directly answer. K max 2 will be, subtracting, after subtracting, energy is 2.5. Work function is 0.5. So K max will be 2 electron volt. Is it clear? But they are not asking me the ratio of kinetic energy. They are asking the ratio of velocities or speeds. So K can be written as half m v1 square divided by half m v2 square is equals to 0.5 divided by 2. I have changed the kinetic energy in terms of speed. Half m will be cancelled. So that will be v1 by v2 whole square is equals to, you can divide it, that is 1 by 4. That is 1 by 4. So v1 by v2 will be 1 by 2. Which is the correct option? Option number B. This is again a very important question. Mark it as important. It was not asked in the last few years. So mark is as very important. Now I am saying, remember one formula. The question, read the question, or you can see the solution after the class is over because I am doing it a little bit quickly. The number of photons per second on an average emitted by the source of monochromatic light. Wavelength is given when it delivers the power of something like this. One thing that you should remember, that number of photons emitted by a source, number of photons emitted by a source N is equals to P by E. Out of this, P is the power of the source and E is the energy of one photon. Remember this formula. N is equals to P by E. N is the number of photons. Now just place the values and you will get the answer. So N is equals to P is given as 3.3 into 10 raised to the power minus 3 watt divided by energy is what? Hc by lambda. Now one thing to be very clear. This Hc by lambda, if we put Hc as 1240 and lambda in nanometer, then it will give energy in electron volt. But in this equation, the power is given in watt, that is joule per second. So there will be difference in units. One is in joule, the denominator will be in electron volt. So I am not using that 1240 term. I am using the standard values. E is Hc by lambda. If I put the value, H is 6.6 into 10 raised to the power minus 34. P is 3 into 10 raised to the power 8 divided by lambda. Lambda is 600 nanometer means 10 raised to the power minus 9. After solving, you will get the answer. And it is very clear that it can be very easily calculated. 3.3, 2 times 236, 600. That will be something 10 raised to the power 16. You can calculate that. Answer this question and we will leave the class. Answer this question. There are three curves A, B, and C. Out of this, before reading the option, what's your mind says about A and B? Which is the quantity which is changing in A and B? Which quantity is changing in A and B? Which quantity means whether it's intensity or frequency? Which quantity is changing for graph A and B? Very good, Gauri. Intensity is changing in A and B. Very good. And which quantity is constant in A and B? Because you can see that stopping potential is same. If stopping potential is same, that means frequency is same for A and B. Very good. Very good, Gauri. So now read the options. Option says curves A and B represents incident radiation of same frequency. That is very clear. A and B have same frequency. Very good. But of different intensity. But of different intensity. Very good. That means statement 1 is correct. Now let's check further few statements so that we can be very sure we can learn something. Curves B and C represents incident radiation of different frequencies. Now identify where is B and C. B and C, they have different stopping potential. That means this part is two different frequencies and different intensities. But B and C, you can see, have same saturation current. That means same intensity. That means this statement becomes wrong. Similarly, curve B and C represents radiation of same frequency. B and C. B and C don't have same frequency. That means this statement is again wrong. Curve A and B represent incident radiation of different frequency. A and B, this is again wrong. They are showing same frequency. So which option is correct? Option A is correct. Now take the screenshot of this one. Done. And this one. These are very easy questions. Solve it. Delete, very good. A option is correct, very good. Now I think it's done. I'm ending the session. हैप्पी ईस्टर बच्चा, हैप्पी ईस्टर। बाय एवरीवन।